defect. So if we have an atom, we'll do helium just because I can't bother to draw too much. Right, and if we compare this to the individual individual constituents, so we've separated it now into its separate constituents. The mass of this
Oh yeah, is it because the energy is released or something like that?
it is, but why and where and how?
It's released, so it turns into mass.
What you need to be a lot more specific about the energy is released.
Because of the E equals mc squared equation, then the energy is transferred into mass.
Yes, you're getting closer, but that's not the full answer. So how do we get from here to here? Right, what do we have to do? We have to put in energy. Right, why do we need to put in energy? We need to break apart. I'm going to put bonds, and bonds is not the right word to use here, right? Because bonds typically means chemical bonds, right? But it's a kind of a way into really getting this clear, right? We're breaking apart the bonds that hold the nucleus together. Right, now it's not bonds, obviously. What is holding the nucleus together? What force is responsible? It's the strong force. So we're doing work against the strong force, which is holding it together. Now, the reason I put bonds and I put it in quotation marks is because if you think about what do you need to do to go from a solid to a liquid, and then from a liquid to a gas, right? You need to put in energy, don't you? Where does the energy go? The energy goes into breaking the bonds, right? And I think we're quite happy with that idea. The energy goes into breaking the bonds. So if you think about this kind of analogy, and then we think about a state, a temperature breaking the bonds. So if you think about this kind of analogy, and then we think about a state, a temperature time graph, right? We know we can heat a solid. Then in the phase change, the temperature is constant. Then we heat it. The phase change is constant. We heat it again. Okay. So during these parts here, right, this is where the state change is happening, and the temperature is constant because the energy is going into breaking the bonds rather than increasing the kinetic energy and therefore increasing the temperature. So when we put in energy here, that energy is going into basically breaking apart the strong force. Right now, when it's separated completely, right, because they're really far apart, there is no more strong force effectively. Okay, so here they're too far apart for the strong force to have effect. So where does that energy go? Well, now Abella's answer is good, right? Now we can apply it. The energy has gone into mass, right? E equals mc squared. So we've gone into mass. So you have to talk about this bit first. Energy is put in to do work against the strong force to pull it apart. When they're apart, that energy goes into their mass. If we go the other way, right, some of their mass goes into basically the bonds. It's not the bonds, but it goes into the strong force, the energy that holds them together. But this, I think, is a really nice analogy because it's very, very similar. Now, I don't know if you remember, or you may not even have done this because it's not on the syllabus. But if we zoom in and if we look at a single proton, okay, what is the quark structure of a single proton? It's up, up, down. Okay, what happens if you try to remove one single quark from the atom? So what happens if you try and get this one and you try and pull it out? So it's just up, up, and down's over here. Does anyone remember what happens? Nabil?
Is a new quark made?
Exactly. Why?
Because the energy applied turns into mass, which forms the new quark.
Yeah, exactly. So large energy needed, and then new quark formed. So this is really interesting because with quarks, you can't have quarks on their own. You put in so much energy, it makes new quarks. But it's exactly the same idea. This is exactly the same as this, right? It's just a different context, different example, right? And here we're very much forming new particles, but here we're just adding the mass. So the next term, which is a little bit simpler to define and remember, is the binding energy. What exactly do we mean by the binding energy? And do you remember?
Is it the work done to separate the nucleus into its constituent parts?
Yeah, perfect. All right. Importantly, you remember the full definition, which is obviously into its constituent parts. Good. So the little bit that Miss Lee wanted me to just go over was this graph of binding energy versus nucleons, which for me, I always found this one of the most fascinating graphs that I think we ever looked at. So we've got number of nucleons and the binding energy per nucleon. Now, binding energy is a really simple concept, but I don't think this graph is completely obvious. I think it does require a little bit of thought about exactly what it means and what it shows. Irma, would you be able to give us a brief explanation of what this graph shows? Okay, Amir, would you be able to give us a brief explanation of what this graph shows?
It shows the essential number of energy required to keep the nucleons together against the number of nucleons. It
does. So do you remember what element is at the top here?
I don't know. Carbon?
It's not carbon.
Fe, gold?
No. Adala?
No.
Iron.
Iron, good. Right. It's worth remembering that this is iron right at the top, right? Because iron is really special because it's at the top. So, I mean, sorry, I did interrupt you there. What does this mean, therefore, about the iron nucleus? What's special about being at the top?
It requires the most amount of binding energy
To
keep the nucleon together.
Yeah, I mean, yeah, effectively, yeah. I probably wouldn't use those words myself, but yeah, you're not wrong. So I would talk about it as the most energy to separate the nucleus. Now, we can make this even more simple. We can just say it's the most stable nucleus. Okay. So what else can we learn about this graph? So if we go either side of iron, these elements are not as stable. Okay, so if we go this way, they are less stable. And if we go this way, they are less stable, effectively. Now, it doesn't necessarily mean they're radioactive, because we know iron isn't radioactive. But what does it mean? It means that ideally elements want to get to iron. If all elements could be iron, they'd actually be really happy because they're the most stable. Okay, they have the most energy per nucleon to keep them together. So this does then start to mean things. So particularly when you go up here, right? So when you get really far up here, you get to uranium, right? And you get to the radioactive elements. So we know these are unstable. We know that these ones, they don't have enough energy to keep the nucleus together. Well, they're just too big. So what do? These elements, they want to go this way and become smaller. So they give out a particle, maybe an alpha particle, and then they move up this curve. And they become more stable. Now, in reality, when you get to lead, that is generally where they become stable again. That's the kind of the last stable element, right? So what's signified by this difference? So if the uranium atom decays and it moves up, what's special about this difference here? Nabil, what's special about this difference here?
I'm not sure.
Anyone else, Abdallah?
Wait, can you repeat the question again?
So if you have a radioactive element and it decays by an alpha particle and it moves up this curve a bit to something else, what is special about the difference in height that's moved up on the y-axis?
I'm not sure.
So it's obviously a change in energy, isn't it? It's a change in the binding energy per nucleus. If this doesn't have much energy holding the nucleus together, this has more energy holding the nucleus together. So there is an energy difference here. All right, so this is a change in energy. And effectively, it's the energy that's given out, right? So they become more stable, they have more energy per nucleon, all right? And therefore, there is obviously going to be a change in the mass defect and the difference between the energy that the constituent parts have and the energy that these parts have here as well. Right? Because what we've done is we've emitted an alpha particle or a beta particle, something from the nucleus, right? And we've removed energy from the nucleus, right? So and you might think, well, hang on, we're just losing energy here, right? Where's it going? But we're removing excess energy from the nucleus, and the remaining ones are more stable. The remaining ones have more energy between them. Right, so it's like there's a limited amount of energy to go round, and all the nucleons are fighting over it. Right, when they're too big, they're fighting over it, and there's not enough energy to keep them together. So they just kick someone out of the room with not a lot of energy, and then the remaining ones have more between them. So this side of iron, right, when things are decaying, right, we tend to label this side of the graph with fission, right, which is like splitting up or becoming smaller. So the elements want to become smaller and go this way. And we're going to talk about fission later. If we look at the other side of iron this way, right, it's obviously going to be the opposite thing. Things want to therefore join together and become bigger and bigger and bigger until they get to iron. So this side corresponds to fusion. So we'll talk about fusion in more detail next week, I think. So, but we know in a bit of it, don't we? We know that hydrogen is here. We know that helium, we know that lithium, etc., is going up this way. And if we get two hydrogen atoms and we make them into helium, right, we know that we give out a large amount of energy. Which is why we want to use fusion as power stations, because it could be a really clean source of electricity. Right. So again, we have to think, right, these don't have much energy per nucleon holding them together. These have more energy per nucleon holding them together. So as we're going up this way, again, we've got some energy difference. Delta E is probably best. Delta energy, which is the energy given out in fusion. Now, immediately from this graph, right, we can tell which one of these processes, fission, splitting up, or fusion, is going to give us the most energy. Right, it's obvious, isn't it? Fusion, because it's a much steeper graph. So again, it's another reason why fission is so sought after. There's so much research going into it, because not only is it clean, there's no radioactive waste, but it will just give us so much energy. There are drawbacks. It's really hard to do. We haven't figured out how to do it yet. Right, but why let that stop us? Now, there's one other thing I think is really important to draw attention to in this graph. Okay, this graph I've obviously just drawn as a nice smooth curve. It's actually not that smooth like this. If we actually start plotting the individual elements, you start to see this kind of pattern. Okay, so you get a nice smooth curve, and there's a couple of ones that stick out. Do you remember from yesterday, or do you know any of these ones that stick out, particularly this one here? Feel free to type it in the chat if you've got any suggestions. Okay, so the first one that is really off the curve, right, that's really, because it does this, is helium. Then the next one is carbon, and then this one here is oxygen. Right, they stand out. And now helium is particularly interesting, right, because what this means is it has a particularly high binding energy for each nucleus. So it means that helium is particularly stable, right, which goes on to explain what we already know, right? Why do large nuclei give out alpha particles? Why don't they give out, 3 protons and 3 neutrons? Why don't they give out 1 proton or 5 protons? They give out an alpha particle, 2 protons, 2 neutrons, because it's very stable. It's the best way to get rid of energy quickly, right? Because it's a really, really stable arrangement. Okay. And it also therefore means that any multiple of this is also going to be really stable. So what is helium? Helium is 4-2, so twice the protons compared to twice the neutrons. So carbon-12 has 6 protons, 6 neutrons, and oxygen-16 has 8 protons and 8 neutrons. They're basically multiples of helium. So these are all, again, particularly stable. Now that obviously breaks down, when you get up here, it breaks down, right, because you need extra neutrons to make up for the repulsion of the protons. But for small numbers of nucleons, these are really, really stable, right? And And if you look at the full graph of this, you can probably pick out a couple of others that are just slightly above the curve. All right, so it goes to show you, I think, my love for this. There's so many little things you can pick out from this one graph, actually branch into a huge amount of physics and huge different areas of physics. Okay,